welcome back to the channel. Today let us continue with the part 2 of quantum mechanics. If you haven't watched part 1, then you can refer to the playlist in the description where you will find all the topics related to applied physics. Quantum mechanics introduces us to a revolutionary concept, the Schrödinger wave equation. Just as Newton's laws describe motion in classical physics, this equation reveals how quantum systems evolve over time. It's not about tracking individual particles, but understanding their wave-like behavior. Think of it as a mathematical lens that allows us to peek into the mysterious world of quantum mechanics, where particles dance between waves and probabilities. This equation is our gateway to understanding the fundamental nature of matter at its smallest scales. Let's dive into the one-dimensional Schrödinger wave equation. This complex formula might look intimidating, but it's essentially a description of a particle's quantum state. The key components include the wave function psi, which represents the particle's quantum state, and v, x, which describes the potential energy. The imaginary unit Ig and reduced Planck's constant are crucial mathematical tools that help us navigate the quantum realm. This equation allows physicists to predict and understand the behavior of quantum particles in a simplified, one-dimensional scenario. The time-independent Schrödinger equation is a simplified version that focuses on the spatial characteristics of quantum systems. When we remove the time dependence, we can concentrate on understanding the spatial wave functions and energy states. This approach is particularly useful for studying stationary quantum states, where the system's energy remains constant. It's like taking a snapshot of a quantum system, freezing its wave-like properties to examine its fundamental characteristics. Eigenvalues and eigenfunctions are fundamental concepts in quantum mechanics, particularly in the context of the Schrödinger equation. The time-independent Schrödinger equation is used to describe the quantum state of a particle in a potential field and is given by the second derivative of the wave function with respect to position multiplied by negative reduced Planck's constant squared over twice the particle's mass, plus the potential energy function times the wave function equals the total energy times the wave function. Eigenfunctions, represented by phi x, are unique spatial wave functions that describe a quantum particle's state for a specific potential energy. Eigenvalues are the corresponding discrete energy values associated with these functions. Imagine them as special keys that unlock different quantum states, each with its own distinct energy signature. They help us understand how particles behave in different quantum environments. Eigenfunctions have several important properties in quantum mechanics. Normalizability. Eigenfunctions must be normalizable to represent a valid quantum state. This means that when you integrate the square of the eigenfunction over all space, the result should equal 1, ensuring the total probability of finding the particle is 100%. Orthogonality. Eigenfunctions corresponding to different eigenvalues are orthogonal to each other. In other words, if you multiply one eigenfunction by the complex conjugate of another and integrate over all space, the result should be 0, ensuring no overlap between different quantum states. Quantization. For certain potentials, the eigenvalues are quantized, meaning the particle can only occupy specific, discrete energy levels. An example of this is the infinite potential well, where the energy levels are determined by the width of the well and the particle's mass. Eigenfunctions and eigenvalues are crucial in quantum mechanics. Eigenfunctions describe the spatial distribution of a particle's wave function, often showing sinusoidal patterns, especially in systems like an infinite potential well. Eigenvalues correspond to measurable quantities, such as a particle's energy. By solving the Schrödinger equation, we can obtain these eigenfunctions and eigenvalues, which in turn help predict the behavior of quantum systems. They determine the quantized energy levels, allow for the analysis of quantum state transitions, and help interpret the probability of a particle's location. Essentially, eigenfunctions and eigenvalues reveal the discrete nature of physical systems and provide a deep understanding of the underlying quantum mechanics. The infinite potential well is a classic quantum mechanics model that helps us understand quantum confinement. Imagine a particle trapped in a box with infinitely high walls. It can only exist in specific, discrete energy levels. The wave functions in this scenario are sinusoidal, creating standing wave patterns. Each energy level corresponds to a unique wave function, demonstrating how quantum mechanics quantizes energy in confined spaces. This example beautifully illustrates the fundamental principles of quantum confinement. Expectation values are the quantum mechanical way of understanding average measurements. For position, momentum, and energy, these values provide a statistical interpretation of a quantum system's behavior. Unlike classical physics, where we can precisely measure properties, quantum mechanics gives us probabilistic averages. It's like predicting the most likely outcome of a quantum measurement, bridging the gap between quantum uncertainty and classical predictability. A free particle in quantum mechanics behaves differently from classical physics. Its wave function spreads out, representing the particle's probabilistic nature. In the case of a free particle, the potential energy Vx is zero. This simplifies the time-independent Schrödinger equation to focus solely on the kinetic energy of the particle. The simplified equation can be expressed as the second derivative of the wave function with respect to position, multiplied by a constant involving Planck's constant and the particle's mass, equating to the particle's energy times the wave function. The solutions to this equation are plane waves, which can be written as a combination of forward and backward traveling waves. These solutions are characterized by a wave number k, which is derived from the particle's energy and mass. The energy of a free particle is continuous and depends on the square of the wave number. In the case of an infinite potential well, the potential energy Vx is zero inside the well and infinite outside. This creates a one-dimensional box where a particle is confined. The boundaries of the well are at positions x equals 0 and x equals L, and the particle cannot exist outside these limits. The wave functions phi and x, representing the particle's state, must be 0 at the boundaries. These wave functions take the form of sine waves, given by sin n pi x by L, where n is a positive integer. The energy levels E and are quantized, meaning the particle can only have specific energy values, calculated based on the particle's mass, the well width, and Planck's constant. The finite potential well introduces more complexity to quantum systems. Unlike the infinite well, this scenario allows for both bound states, where particles are trapped, and scattering states, where particles can escape. The solutions require advanced numerical techniques or boundary matching methods. This model demonstrates the nuanced behavior of quantum particles, showing how energy barriers can partially confine or allow particle transitions, bridging the gap between complete confinement and total freedom. Quantum tunneling is a truly mind-bending phenomenon that defies classical physics. Imagine a particle encountering an energy barrier that, according to classical mechanics, it shouldn't be able to cross. Yet, in the quantum world, this particle can miraculously pass through the barrier. This occurs due to the wave-like nature of particles, where their probability of existence isn't confined to a single location. The tunneling probability depends on the barrier's height and width, creating a fascinating probabilistic pathway through seemingly impenetrable obstacles. Quantum tunneling isn't just a theoretical curiosity, it has profound real-world applications. The Scanning Tunneling Microscope, STM, leverages this quantum effect to image surfaces at the atomic level, allowing scientists to visualize individual atoms. In astrophysics, tunneling plays a crucial role in nuclear fusion, enabling protons to overcome Coulomb barriers in stars. These applications demonstrate how quantum mechanical phenomenon can bridge microscopic behavior with macroscopic technological and astronomical processes. The Scanning Electron Microscope represents another marvel of quantum interactions. By focusing an electron beam on a sample surface, it creates high-resolution images through quantum interactions. Secondary electrons are emitted and captured, generating detailed visualizations of surfaces. This technology has revolutionized multiple fields, from materials science to biological imaging and nanotechnology. It's a perfect example of how understanding quantum mechanics can lead to groundbreaking technological innovations. The quantum harmonic oscillator is a fundamental model that helps us understand molecular vibrations. Unlike classical oscillators, quantum systems have discrete, quantized energy levels. The potential energy follows a specific mathematical form, and the energy levels are not continuous, but come in precise increments. This model reveals a profound quantum principle. Even at absolute zero, a system cannot have zero energy, introducing the concept of zero-point energy. In the quantum harmonic oscillator, energy is not a smooth, continuous spectrum but a series of distinct steps. The ground state energy, representing the lowest possible energy, cannot be zero due to the uncertainty principle. Each higher energy level is a precise multiple of the fundamental frequency. This quantization demonstrates how quantum mechanics fundamentally differs from classical physics, introducing a stepwise nature to energy that was previously unimaginable. Wave functions in the quantum harmonic oscillator are elegantly described using Hermite polynomials. These mathematical expressions capture the probability distribution of a particle's position in the oscillator. Each wave function corresponds to a specific energy level, creating a beautiful mathematical representation of quantum behavior. The normalization constant ensures that the total probability across all space remains constant, a fundamental requirement in quantum mechanics. Zero-point energy represents the minimum energy a quantum system possesses, even at absolute zero temperature. This fascinating concept emerges from the uncertainty principle, which prevents both position and momentum from being exactly zero simultaneously. Zero-point energy explains complex phenomena like superfluidity and vacuum fluctuations. It sets fundamental limits on how cold a system can become, revealing the inherent dynamic nature of quantum systems. We have reached the end of this video today. Thank you for watching, and don't forget to like and subscribe for more tutorials on other exciting topics.